Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I think we've had a form out there for people to submit questions and topics you'd like me to try and talk about. And I see there are a few things that have come in there. All right, there's one from Stuart here, suggesting spatom as a portmanteau of space atom of space. Well, I haven't heard that term before, so that's a new one on me. I think this term atoms of space is one that we've started to use in connection with our physics project. Maybe I should explain a little bit what we mean by atoms of space and what kind of the story behind that is. You know, I think I've talked about this a few times before, but my understanding of these things gradually progresses as our physics project has moved forward. And for those who don't know, the traditional sort of leading theories in physics date from about 100 years ago. The general relativity is the theory of gravity, and quantum mechanics and quantum field theory as the theory of very small things. And in the last couple of years, much to my surprise in many ways, things that I've been kind of working towards for several decades have kind of converged to the point where it looks like we have a serious other step in understanding kind of the low-level structure of our universe. It's very exciting. But kind of the place that starts is a better understanding of space. And by space, I mean the thing that exists everywhere in the universe that we move around in, the thing that has, 3 dimensions roughly that we can move in. And the thing that people have kind of assumed about space for basically 2,000 years is that space is just sort of a background and things get put in space. Wherever you feel like putting something, you can put it there. And that there's no substructure to space. Space is just like the blank sheet of paper where you get to place points wherever you want. Okay, so one of the sort of first things to realize in our project is the idea that space isn't actually just this background where you can put things anywhere you want. Space actually has its own internal structure. And kind of a good analogy for this is a fluid like water. You might think that, you pour some water, it's just a continuous fluid, it just pours continuously and so on. But in fact, for the last 150 years, we've known that water consists of discrete molecules. And if you kind of look sort of a fine enough level under a powerful enough microscope, you'll basically be able to see water is not just a continuous fluid where you can sort of put something anywhere you want in it. It's made of discrete molecules. That's something that had been kind of, people had wondered back in ancient Greek times and so on, a couple of thousand years ago, people had wondered, is the world actually made of atoms, as they called them? Atom means a thing you can't split, Greek for that. And so it's sort of a tomos, I guess, not splittable. And so, of course, it was a big deal in the 1930s and 40s and so on, when it became clear that one could actually split what we thought of as atoms of material stuff, like hydrogen atoms, or, well, that's not one you can split, but uranium atom or something like this, that those were splittable. Those are atoms of material objects. Those are atoms of matter. The question is, are there discrete atoms that make up everything, that make up space that exists everywhere in the universe? Or is that something that's just this continuous background, so to speak? So the thing that is sort of the foundation of our physics project is the idea that no, there actually are atoms of space. What are they like? Well, the only thing you can say about them is they're kind of discrete elements. They're like, each one you could think of as being, you could give it a name, you could number it, you could do whatever you want. But the only thing you know about it is that it's distinct from other ones. And then the only thing that is determined about these things is how they're related to each other. So it's as if every atom of space is like a person and they're connected in a friend network. And all you know is that friend network. You don't know, for example, there's no notion of what position is this atom of space at, what position is that one at, because there is no space to put these things in. It's just this network of sort of disembodied atoms of space that are related by these connections. And so you can draw this big graph where you're a big network, where you have points and you have connections between those points. That's kind of the structure that represents space on a very, very small scale. We don't know exactly how small the scale is. We think it might be a trillionth of a meter. So quite small. And by the way, the smallest we've ever been able to probe with particle accelerators, which are kind of the analog of our most powerful microscopes, so they don't look much like microscopes. They're things that accelerate particles to high energy and crash them into other particles and see what happens. But the smallest scale that one's been able to reach, that one's been able to probe with those is a trillionth of a meter. Whereas what we're thinking, the actual scale of the discreteness of space is trillion, many times of a meter. So much smaller than that. So the thing that, the starting point is this idea that what's at the lowest level in our universe is just this giant network of atoms of space. And I was sort of reluctant at the beginning to call them atoms of space because I thought people would get confused with atoms of matter, which are things actually made of protons and neutrons and electrons and things like that. What we're talking about is the very lowest level stuff of the universe, the fundamental thing that space is made out of. And one of the things that is sort of more extreme in our model of physics is that actually everything is just made of space. That the only thing that exists in the universe is space. It's kind of like if you have a fluid like water, you can have a little vortex where you have water circulating around, and that vortex can have a certain persistence. It can move through the water and so on. And that's what we think particles like electrons and so on are really like. They're kind of like little persistent structures within this network that represents the structure of space. And so sort of everything in our universe is just made of space. It's just all features of this network that represent space. And one of the things that then happens is the progress of time is kind of the progressive rewriting of this network. So there are rules that basically say, if there's a little local piece of network that looks like this, it should be rewritten to one that looks like that. And those things are happening trillions and trillions and trillions of times every second. Every piece of space is getting progressively rewritten. And to say that there's a particle is to say there's some structure, like the vortex in the water, even though the molecules of the water are bouncing around at a small scale all over the place, this vortex is still surviving in the water, and it still persists for a long time, a very, very long time relative to the time it takes the molecules to collide around in the water. So the thing that actually something I've been working on a bit recently is one of the things that's really surprising about things that happen in the universe is that pure motion is possible. That is, it is not obvious if everything is made out of these atoms of space and all these details of the detailed connections of atoms of space, it's not obvious that anything that you could take this thing that's made out of all these detailed connections and just expect it to be moved to a different place and stay more or less the same. Because in our theory, basically, whenever I move, the atoms of space that make up me are new, different atoms of space. So it's not obvious that something that corresponds to me, so to speak, can exist at that new place and a new position. Now, I should say that one of the big features of our models is that when you look at the smallest scale, all you see is atoms of space and all sorts of detailed rewriting of connections between atoms of space and so on. But if you zoom out, trillions and trillions of times, what you will see is something that seems like ordinary space as we experience it. It's very much like what happens in something like water. If you zoom all the way and you see a bunch of molecules bouncing around, if you zoom out, you see just a continuous fluid that's flowing like water does. And so it is with space. And most of the activity of space in our universe, in our theory, consists in kind of the rewriting of these detailed patterns of connections between atoms of space. In fact, the huge, vast majority, the amount of activity, the universe, the amount of effort the universe puts into rewriting the structure of this network, rewriting these things at the level of atoms of space, is trillions and trillions and trillions of times larger than everything that is relevant to anything we see about particles and motion and all those kinds of things. Most of the activity of the universe is maintaining the structure of space. And the things that happen within space are just tiny little details on top of this big activity of maintaining the structure of space. So for example, in the case of motion, what we're saying is there's this big activity of maintaining the structure of space, and we can have a thing that exists sort of on top of all that activity that can be just moved from one place in the universe, from one place in space to another, and can wind up being the same kind of thing. And it is extremely non-trivial that that's possible. And it's something that is deeply wound up, I think, with questions about how we as observers of the universe operate, and the fact that our consciousness is sort of based on the idea that we think that there's sort of a continuous thread of time that we exist on, and so on. All of these things are mixed together to lead to this possibility of pure motion. And by pure motion, I mean, you move something around in space, it doesn't change much. It doesn't change perceptibly. Now, one of the things that happens is in our models, as in the traditional theory of gravity, space, there's curvature in space, which means when your gravitational field consists of a distortion of the structure of space. And so when you're near a massive object, it generates gravity, it distorts the structure of space. If you're near a black hole, it distorts the structure of space a lot. And in fact, if you're very near a space-time singularity of the kind that exists at the center of a black hole, you distort space infinitely. And when you get to a place like that, pure motion is no longer possible. If you take a thing, like a spacecraft or one of us or whatever, and you are near a space-time singularity, and there isn't a space-time singularity for a long way around us right now. Don't know where the nearest one is. It might be, that's an interesting question actually, where the nearest black hole is, but it's certainly maybe 500 light years away, something like that, maybe more, I'm not sure. But it's not, you have to go a long way out. None of the nearby stars seem to be black holes. You have to go a long way out to get one. So we're not in danger of this happening to us anytime around here. But in any case, the nearer space-time singularity, if you kind of go near that space-time singularity, the structure of space sort of disintegrates there, and there is no possibility of pure motion. Any object is completely shredded as it goes past that singularity. So that's kind of the, so this notion of atoms of space is the thing that underlies this whole set of ideas that leads to the structure of space and so on. And one of the things that's really kind of exciting is, just as when you study something like water or air, there's a certain way in which you can make a model for how all these molecules bounce off each other and sort of collide at a small scale. But when you zoom out to a large scale, you find out that there are certain overall laws that are true about gases, overall laws that are true about the flow of fluids, and you can derive those independent of the details of how these microscopic molecules work. Well, that derivation of the fluid equations, for example, from microscopic molecules, the analog of that in our model of space with atoms of space and so on, the analog of doing that leads you to sort of a collective continuum equation for how space behaves. And it turns out the equations you get are exactly the equations that Einstein proposed in 1915 to be the equations that describe the structure of space-time. So in other words, from that underlying structure of just talking about atoms of space and connections between atoms of space and so on, when you zoom out to a large scale, you discover that you get exactly gravity in the way that we observe gravity to work in our actual universe. And that was the core of the theory of general relativity back in 1915. So that's a pretty cool thing. And it's certainly something which back in 30 years ago made me think maybe I was sort of vaguely on the right track. I figured that out. Maybe I was sort of on the right track in figuring out what's kind of ultimately underneath the physics that we see today. Now, one of the things, there's a lot more to say about our physics theory. Let me not go into that in detail here. But I will say in terms of this whole atoms of space thing, this whole notion of this underlying structure of these abstract things that are connected in this graph and are updated and so on, and that are updated in many possible ways. That's a whole other story that leads to quantum mechanics and so on. That whole story of sort of all these different kinds of updatings of all these kind of abstract elements, that story turns out to have a much more general version that I figured out fairly recently, that leads to this thing we call the Roolead. Roolead is a very strange creature. The Roolead is a very ultimate creature in some ways. I shouldn't say creature, it's an abstract kind of thing. But here's how you think about it. You think about some rule that you might use that you can just follow the rule, you apply it again, again, again. It's like how a computer works. You can think about it as being that rule, the application of that rule as being a computation, because it's just like your computer, it's just applying these instructions, applying them again, applying them again, applying them again to do what the computer does. But now imagine that you start off all possible computers from all possible initial conditions, and you just let them all run. Well, one of the things that will happen is two computers that may even be different computers with different initial conditions, it will turn out that they will, at some point, they will end up just evolving to the exact same state, just because that's what can happen. And so you get this giant sort of entangled graph of all possible computers evolving from all possible states for an infinite amount of time. That's a giant entangled thing. And that's this thing I call the Roolead. And that thing sort of represents all possible computations. It represents, in a sense, all possible formal processes. And the thing that is sort of exciting is that what we've kind of realized is that the way that we observe the universe is essentially by taking, we exist, we're sort of sensing some slice of this giant Roolead of possible computations. And the particular slice we take depends on it depends on us. It depends on the fact that, we have certain sensory systems and eyes that can sort of form images, and we have minds that kind of think that we have persistence through time and so on. Those features force us into sampling the Roolead in such a way that we observe physics of the kind that we actually know to be correct from sort of observations, experiments in physics. So one of the surprising and very abstract things is that when we do mathematics, we're actually also sampling this same Roolead, but in a slightly different way. So it's like there are physical observers where we experience the physical world, and when we do abstract mathematics, pure mathematics and so on, we are essentially sampling the same Roolead of all possible computations, but we're sampling it in a different way. But one of the things that I've recently been studying quite a lot is we as observers of the Roolead have certain limitations. For example, we can't do an arbitrarily complicated computation. We are bounded in the computations we can do. We believe we're persistent through time, for example. These are essentially limitations to the way we observe the Roolead. Those limitations sort of affect us as physical observers, but they also affect us as mathematical observers. And that limitation, those limitations of the mathematical observer lead to certain consequences for mathematics. In fact, one of the things that I think is true is the very fact that it is possible to do higher level mathematics, that it's possible to invent abstract mathematical structures and have them be meaningful, happens for essentially the same reason as we can imagine that there is this notion of continuous space, that we're not always thrown down into this lowest level of looking at individual atoms of space and so on. And so the thing that one realizes is that sort of mathematics, the possibility of doing higher mathematics and having sort of mathematical structures of being able to talk about mathematical curves and things like this, not having to discuss mathematics down at the level of its kind of lowest level axioms and so on, that possibility comes from exactly the same place as the possibility of doing higher level physics and the possibility of thinking about the universe in terms of things like space and particles and so on, and not in terms of low-level atoms of space. So this is sort of a recent thing that I've just about to actually put out a big tome that I've been writing. It's a couple of 100 pages long about the physicalization of metamathematics, which is kind of this story of how there's sort of a physical interpretation of what happens in the structure of mathematics. But that means that these atoms of space that we talk about as being the lowest level things that make up the physical universe, there is a direct analog of those in mathematics. And it's actually, they're the same thing. They're both elements of this rule-iad, and the name we're using is EMES, E-M-E-S. It's kind of a sort of a colorless kind of word that means like a phoneme or a morpheme, lots of other kind of things mean elements of things. This is sort of a pure element of anything. So one of the most bizarre ideas is, which I'm not sure I'm going to be able to explain great, but the question might be, what's the analog? If I say an electron is this kind of persistent structure that exists in the low-level structure of space, then what's kind of the analog of that in these other, for example, the rule-iad in general? And one of the most bizarre ideas, recent idea, is the following thing. So we can think of different places in this rule-iad as, you can think of different places in ordinary space as just, we know what that means. They're just different positions in space. And we can get between those positions in space by moving, by this idea of motion in space. Different positions in the rule-iad are also possible. And to get from one to the other, we essentially have to translate from one form of computation, from one way of computing things to another way of computing things. So different positions in the rule-iad, in a sense, correspond to different interpretations of what's going on, different forms of computation. And I think that's very much like what happens between different people, for example. We all have some view of the world and we have some representation of everything, and somebody else will have a somewhat different view of the world and representation of everything. And somehow we can communicate between these. Something persistent, a little bit like a particle, is able to get from one mind to another, so to speak. And what are those things that sort of are persistent and packageable and don't depend on the specifics of an individual mind? And essentially, those are things like words and concepts that we've managed to kind of package up. And we say a word like motion, for example, and the sender of that word might have some representation in their brain for what that word means. The receiver might have some completely different representation, but we've kind of got this transport level of that, just the word, which we can kind of communicate from one person to another. And so the very bizarre kind of, could this possibly be true thing that's sort of at the outer limits of what I'm thinking about right now is this possibility that concepts, the notion of discrete concepts and words for concepts and so on, is related to the existence of discrete particles in physics. So that's about as far out as it gets in terms of sort of relations between different areas. All right, so many other questions we had here. Let's see. Well, let's try a few others here. Gosh, there's so many interesting questions you guys are asking. This is well, let's see. All right, there's a question here. Parmenides. This is more a historical question about whether I ever met a person called Vladimir Arnold. Yes, I have. What do I think of the Erlangen program? I am not sufficiently familiar with it to comment on it. Let's see. Yeah, I should say the thing I was just answering was about as sophisticated, technical, and abstract as it comes. So Aaron was asking a question here. Can spoken language be broken into a set of logical primitives? what attempts have been made to do this, and so on. So there's a question of sort of how is spoken language structured? The first thing to say about it is it's got a certain, well, it's got several levels of structure, but one definite structure is it's got a syntax, it's got a grammar. We know, for example, in English, we tend to have subject, verb, object. You know, the cat ate the fish or something. We've got, you know, noun, verb, noun. And we've got that. So sentences tend to have this kind of grammatical structure, and one can often draw out this kind of trees where a sentence has certain phrases, you know, has some, you know, a collection of words that are a noun phrase, you know, adjective, adjective, noun, let's say, a collection that are a verb phrase that then goes, you know, noun, verb, noun, verb, noun. I think kids sometimes still learn to diagram out sentences. They didn't teach that when I was a kid. In fact, they didn't teach any grammar except for Latin, which is a somewhat simpler language than English. And it's only in adulthood that I've ended up being exposed to the full and elaborate grammar of English, which tends to be expressed in very thick books, whereas the grammar of Latin is expressed in much thinner books. But in any case, so the first kind of thing about sort of the structure of language is it's the way that you put words together to make sentences. Then the question is, what do the sentences mean? The kind of semantics as opposed to syntax of the language. Well, this is something where people have been interested for a long time in, can we make computers understand English text? The question is, what does it mean to understand English text? In a sense, understanding is a conversion from something like English text to something which is a native to the computer understandable thing. Well, people hadn't really had that. And I suppose a big breakthrough that I was responsible for back, what is it, a dozen years ago now, was what we did in Wolfram Alpha, where in Wolfram Alpha, the idea is, you know, you give Wolfram Alpha some input through directly on the web or through Siri or whatever else. You give it input and you ask some question, you know, what is red blended with green? I suspect that would work. Then what we have to do is go from that natural language, from that English, to something which a computer can intrinsically understand. What is that thing that a computer can intrinsically understand? Well, for the last basically 40 years, I've been building this computational language that's now our Wolfram language system, which is a way of representing things in the world computationally. So what that would turn into is something, some sort of word known to the computer, blend, which is some actual computational word in the computational language, Wolfram language. And then there would be some representation of red and green as colors, which are entities understood by Wolfram language, understood by our computational language. And that computational language is then implemented actually on computers. And so then not only can you understand that question is, you know, blend red and green, but then you can actually go and compute what's the result of blending red and green. So in a sense, the big, one of the big breakthroughs of Wolfram Alpha was having a very rich computational language that could describe things about the world. It could describe things about numbers or mathematical formulas or cities or planets or whatever else. All these things are things that are representable in the language and about which we can compute things, whether it's, you know, cities. We also have a lot of knowledge where we know about, you know, the positions and populations and so on of cities, so we can compute the distance between two cities. We're not just looking that up, where we know the positions of the cities, so we can compute that distance. And if we had many cities, we could say, what's the shortest tour you can take between those cities? You first have to know the locations of the cities, and then you have to do a lot of complicated mathematical calculation to figure out what's the shortest path that gets between those. Okay, so in any case, the sort of the big idea there was, can one make this computational language that represents a lot of things about the world? And yes, that's what we've succeeded in doing over the last 40 years. And that's the most of what I sort of do with my life, so to speak, is gradually try to extend that computational language, try to bring more areas of kinds of things that people want to do and things that people want to think about into the domain that can be understood computationally. And it can be understood computationally in a way that is both a good way for humans to formulate their thoughts, to sort of clean up their thoughts, and also a computer can actually run these things and help the human with them, so to speak. So that's been kind of a big effort that, as I say, is the much of what I spend my time doing is building this language and gets used by lots of people to do lots of things. And although I think there's, we're still very far ahead of most of what we built, much more than is than most people know to use, so to speak. But anyway, the objective there is to represent anything in the world computationally and be able to compute about it. Now, one piece we haven't really done is what I've tended to call symbolic discourse language, which is talking about things, just general discussion, just things like, I think the example I tend to give is, I want to eat a piece of chocolate. We have a great representation of a piece of chocolate. We know about all the different kinds of chocolate. We know how big is a piece. We know all kinds of things about that. We know the density of chocolate. We know all sorts of stuff. So we can represent that. But the I want to eat part, we don't have a way to represent that yet. And so one of the things that is kind of in my future development direction is to actually have a computational way to represent things like I want to eat blah blah blah. And in fact, people last really seriously tried to do things like this about 400 years ago. There was sort of a phase when it was very popular to think about what were called philosophical languages, which were going to be languages that represented the meaning of things without using words from specific human languages. It was a time when Latin was kind of going out of circulation as the language of learning, and people were like, well, what's next? Well, we can invent something that's sort of more mathematics-like, that would be a language that could express things sort of independent of the actual words. Well, there was sort of a 400-year hiatus, but we're now in a position to start doing that again. And there are many applications. For example, when you have computational contracts, if you have a legal contract, it's written in human language like English, and it says various things about what should happen and so on. That what has become important, particularly emphasized by things like blockchain and so on, is the idea that you can have a contract that is represented completely computationally, where you have something which is just a piece of computer code, effectively, that says if this happens in the world, then this should happen, and so on and so on and so on. And that's something that symbolic discourse language can potentially be used for. But anyway, so the question then is, what can you represent in the world as it is? What you're trying to represent sort of everything in the world computationally, including things like the way we think about things, the fact that we want a piece of chocolate or something, the description of our mental state, things like this. And so the question is sort of what's involved in doing that? And what you realize is there are certain kinds of things we know about the world that you can encode. So for instance, things we've done very much, already in Wolfram language, things about positions and positions on the earth and sort of spatial position and distances and all those kinds of things. We understand that well. Things about time, the notion of, you've got things in the future, things in the past, things that accurate to the minute, things that accurate to the century, how that all interacts with each other. But there's gradually different kinds of sort of calculi of understanding of certain kinds of things which one has to represent. And that's kind of when I should say that I think the question that was asked here was about logic. So sort of zooming out a little bit here, when we try to represent things that we talk about, I think that our best hope for being able to do that in a way that makes a sort of a bridge between us and computers is this notion of computational language. And computational language is a very rich way to represent things in the world in a form that is accessible to computers. Logic was a particular method for doing something a little bit like that was invented in the 4th century BC, presumably by Aristotle. And it's worth understanding what Aristotle actually did. What Aristotle did was he liked cataloging things. So, he cataloged, types of animals, he cataloged different causes for things. And he also looked at arguments that people made that said things like, it's not true that either A or B. And he knew that that was equivalent to saying it's true, it's not true that like A and B is equivalent to, I have to work this out. See, I'm not good at this, is equivalent to not P or not Q. Is that right? Something like that. In any case, there are these things that you can say just by sort of, by making what one might call a logical argument that is purely a matter of, for example, let's say, very famous one, not P is P. So if you say it's not raining today, then that means it's raining today. And that predicate, what's called a predicate, it's raining, could be absolutely anything. It would be, it's not sunny today, means it's sunny today. And so that's a general principle. It's a general structure of argument that the not something is the same as the thing itself. A little bit of a footnote there. That's that law of double negation is something that is a very tricky issue in general. The examples I've given are rather simple examples where, yes, it really works that way, but there's a whole sort of story of whether it has to work that way. But in any case, what Aristotle did was he said, let's take all these kinds of arguments that people make and let's make an idealized version of these arguments and represent in a way where it doesn't matter whether it's like, whatever it is, Pericles calling so-and-so a toad or whatever, or whether it's, somebody arguing for, the Battle of Salamis or whatever they were talking about in those days. Doesn't matter what the actual subject matter is, it's just a question of the structure of the argument. And that's what logic was intended to capture. But the way that it captured that was very specific, very much just about these kind of straightforward human arguments. It isn't the case that it's not obvious that you can generalize from that to talk about something about physics or to talk about something about human emotions or something like this. It's a particular way of capturing the structure of certain kinds of arguments. Now, historically, the original structure of logic was mostly in terms of what's called syllogistic logic. A famous example of that is all men are mortal, Socrates is a man, therefore Socrates is mortal. That's a typical example of kind of Aristotle style logic. And that got generalized and made more mathematical, particularly by a chap called George Boole in the 1830s. And that led to what's called Boolean algebra, which is what is kind of the raw material from which computers manage to do the sort of logic that computers do and sort of what you build up from in a lot of things that happen in computers. But the thing is that sort of pure logic in the sense of ands and ors and nots and these kinds of abstractions of arguments that Aristotle developed and Boole kind of cleaned up, that's not a good representation of everything in the world. It's a representation of a pretty narrow set of things in the world. And so if you say, let's translate everything in the world into logic, it's just not going to work. And in fact, we can see that rather interestingly in the things we've been doing now in fundamental physics. We can say, where does logic lie in this rouliad of all possible formal systems and this and that and the other? We can say, where is logic? Well, logic is a little piece over in some corner here. The laws of physics, another piece over in some corner. They're not, logic is a fairly specific thing. It's something which captures some aspects of human argumentation, but it isn't some sort of universal representation of all knowledge, for example. That's just not true. And it's something actually we can see with clarity that that's not true when we look at these things about sort of the way to think about fundamental physics and the way to think about the foundations of mathematics. So let's see. There's a comment here. Yeah, the sort of what is language and how to think about language. Yeah, I'm very interested in this question. And, when we have a word and the word red, let's say, that, I imagine what red means because I'm used to the fact that a thing that is described as red has a certain effect on the retina in my eye and a certain, excites certain neurons in my brain, and I call that red. It's not obvious that when somebody else's description, something like red is a very sort of, there's a definite kind of neurological representation of that, in the sense you could, but the question is, when we have a word and it has certain meaning, there's sort of every use of that word has, this particular object is read in this way, this object is read in that way, that object is, et cetera, et cetera, et cetera. Every instance of the word red, if we could imagine that there was this kind of space of all possible meanings of things, all those different uses of the word red will be points in that space. And there's, we could imagine there's this huge sort of space of, where as we move around the space, we move around sort of the notion of meaning. We would have somewhere else in the space would correspond to a meaning that was a dog. Somewhere else would correspond to a meaning that was something different. And as we move around, we're sort of moving around in this meaning space. But whenever we use the word red or the word dog, we're sort of putting a point in this meaning space, and our different uses of the word dog or the word red will correspond to slightly different points in this meaning space. And so then the question is, for a given word, it's sort of a cloud in meaning space. And for example, if a word has many different meanings, there'll be many pieces to this cloud. And if a word gradually changes its meaning over time, the cloud will gradually extend further out and so on. So this is so that's kind of the so then the question of something like, how do you assign these positions in meaning space? How does that work? Well, we don't really know. And we kind of imagine that the word, as it is used in different contexts, we'd sort of be able to deduce from those contexts where that word is in meaning space. There have been attempts to do that using machine learning that are, I would say, rather simplistic at this point. But that's kind of the conceptually this notion of imagine a meaning space. It's not clear exactly what meaning space is, and that's something that I would like to try to clarify. And perhaps thinking in terms of things like this Rouliad and so on gets very, very abstract. But I think that there's a potential way of clarifying that in the perhaps not too distant future, and that will allow us to have a more rigid version of kind of what it means to have what these kind of clusters of meaning are and so on. Okay, so let's see, there are some other questions here. There's a question here, a very different question from Damien. In the future, will we have better designed and optimized cities, homes, everyday objects? It's an interesting question. I think that the first question when you talk about optimized things is optimized for what? So when you look at the layout of a city, for example, there are cities where they just sort of grew up over the course of time, and people kind of added a street here and there, and et cetera, and they're kind of a mess. And then when cars came along, for example, it was all very confusing. Where do you park the cars? How do the cars get around these corners? I remember I've certainly seen, there are walled cities in Europe, particularly, where it's like you can't fit a truck through the walls and things. And they were obviously built long before anybody thought about trucks and thought about that as a purpose for which you might optimize cities. And I think and in general, the sort of the structure of cities was for a long time optimized for people walking around or people with horses. And then, 100 and something years ago, cars came along, and then cars became common. And then sort of lots of things changed. For example, a city which was originally something you kind of could walk around, then there were suburbs that were tens of miles away, perhaps, where, yeah, you could get there just fine with a car. And they were much more spread out and so on, and optimized for cars. And that happened in the US in the 1950s and so on, that sort of growth of suburbs that were kind of made possible by cars. And I think then there are cities where, famously, I don't know, and it might be an apocryphal story, but the streets of Paris, for example, Napoleon made them all straight. So if things went wrong, he could, shoot a cannon straight down the giant city street, so to speak. That was an optimization for something, was sort of make the things straight and so on. I think this question of what does it even mean to optimize kind of the environment we live in? So for example, another thing is people will see some, classical building that has all kinds of decoration and elaborate moldings and things and sort of scroll-like things on it and so on. And they might say, and people did say about 100 years ago now, people did say, hey, let's get rid of all that stuff. We don't need that. It's not optimized. It's not maximally efficient. We could just have a box. We could have all our buildings just be boxes. Well, and so then a lot of buildings got built. That was kind of a style of architecture, this kind of minimal geometrical style of architecture. Turns out, well, some people like those buildings. I think maybe architects like those buildings better than the people who are in them like those buildings sometimes. But in fact, it turns out that humans seem to rather like there's a certain sort of comfort level associated with having these kinds of things that are more decorative. And perhaps the reason for that is because nature is full of decoration. I mean, you don't see a lot of perfect, trees that are perfect cylinders with little spokes coming out of them. Trees are elaborated, decorated things. And so we just sort of being out there in the world get used to this kind of level of kind of complexity for free that happens in nature. And I think that's kind of why it is more comfortable to us usually to see things like architectural forms that have a certain degree of nature-like decoration to them, rather than being sort of pure, in a sense, what you might think of as basic mathematics, geometrical, simple geometrical structures and so on. Those in some sense might be more efficient, but they are not as sort of, they don't seem to be, for most people, as sort of comfortable as things that have more kind of structure and more things, perhaps it's like, that look more like nature and more like things we're used to. I'm not sure. And so this is, again, a complicated thing, an optimization of things, because, if you waited, if everything, if you get rid of everything in nature and you're, it's kind of like the people living in the spacecraft that's going to wherever, and it's going to take 1,000 years and there are multiple generations and all they know is the spacecraft. Well, maybe they would have a different architectural sensibility about things and say, no, actually, when they get to the planet and they start building a city on the new planet or something, they'll be like, of course, we're going to just build these geometrical structures because that's what we're used to. So I think it's a complicated thing to say what makes things sort of more optimized. Now, similarly, when it comes to things like cities, we have, there are questions about sort of how will people get around in cities? How much do people even care about getting around? What, it's been to what extent is it important to people to get around at what speed and so on? And to what extent do people, they're sort of paradoxical in some sense, things you might have thought back, 50 years ago or something, that, wherever people want to get around, you want to get around the most efficient way you can, they drive the car, you do this. And then people realize, oh my gosh, if you drive cars all the time, you never get any exercise. Much better and much more, and you don't produce a bunch of exhaust and so on if people are riding bicycles instead. And so what you thought was an optimization about make everything really good for the cars turns out to be not quite what you thought was so good, and then you're building bicycle trails and things all over the place. And I think it's so if we look at sort of the future of cities now, there are clearly sort of coming things, self-driving cars, clearly a coming thing. Not clear how well drones are going to play into all of that. I mean, there are endless experiments now about sort of air taxi type things where, because the big thing that happened was the possibility that came about from sort of computer control of flight together with better battery technology made it possible to have drones that could just be, like quadcopters with four propeller-like things that would just, do the things that drones do and just take off vertically and fly around. And I've seen a bunch of demos of no, not real demos of the thing on the ground, mostly. Yeah, I think it's always been. I've seen them fly, but not with people in them. Right, of drones that are sort of the air taxi, the future air taxi drone type thing. So if that worked out, then that would again change the structure of cities. If people, were able to hop from here to there, that changes how you need to set up your cities. I mean, there was a time, even when I was a kid, where people were saying helicopters are the future. And you would see in the kind of the predictions of the future from back in the 1960s and so on, you would see everything flying around. Everybody was flying places. Cars were a thing of the past. It's like, you had the family helicopter rather than the family car, so to speak. And that didn't come to pass. Why didn't it come to pass? It's quite subtle and quite dependent on technology. I think one of the main reasons is that helicopters are expensive to maintain, difficult to fly. At the time, there was no kind of possibility of automated controls for helicopters. It was a human kind of thing, and helicopters are difficult to fly. They tend to be they're quite unstable in many cases, particularly when you're landing a helicopter. There's a time when the helicopter is sort of pushed up by air bouncing off the ground, and there's time when the helicopter is kept up by air being pushed down from its rotor. The transition between those is complicated. Lots of different things like that. So helicopters were, I think, also the cost of maintaining a helicopter is very high, of making sure that all the parts are working correctly and so on. And so helicopters didn't catch on. And had they caught on, probably cities would be very different even today. If drones catch on, there'll be a different story. If that's one thing. If for example, sort of augmented reality, video conferencing kinds of things get better, again, that might change the situations in which people will choose to, even go across town to go and see somebody, such kind of thing. I mean, I think, in this pandemic, there have certainly been some changes of habits about the ways that people interact, and for better or worse. But I think that many of those will continue, and that will probably have an effect. But so then there's sort of the question of sometimes, in cities there've been times when it's like, we've only got a small amount of land for the city. Where can we build? Let's build up. And so you get big skyscrapers and so on. And then you get kind of, I want a better view than everybody else, maybe some of the time. When I was a kid, people were always talking about, oh, we'll build cities in the ocean. Well, hasn't happened. Turns out nobody really cares. Turns out that's not, that's not a thing that we need to do or particularly want to do. Similarly, people, there have been sort of theories where, oh, who needs sunlight? Who needs this or that? We'll build these, closed boxes and so on. And that hasn't typically worked out very well. But so, I think there have also been theories about how at different times, people have said, oh, we really want to be, everybody collect in the cities. Cities are great places to be. At other times, cities have seemed like there are all kinds of problems in cities and everybody wants to be out of the cities. It seems to vary, and it seems pretty hard to predict what you are optimizing for. I mean, for example, one of the things that people, at different times, people have said, let's make cities that just have more room for cars. And then people say, no, we really like green spaces in cities. Let's make sure that there are, big parks in cities and so on. And it's kind of, goes different things seem to happen at different times. And I think it's really very much a question of kind of what people think they want and how the evolution of what they think they want is affected by the technology of what's deliverable. For example, people might say, I always want to be able to, let's say there's a city that's built in a place that gets very cold in the winter. So like Minneapolis, for example, I think has pretty much, continuous sort of many parts of it have sort of continuous in places where you can kind of just walk inside without having to go outside. And that's something that's sort of optimized for that situation. And I think one can imagine sort of other kinds of things like that once they're technically possible are things that, or for example, let's say that all deliveries could be made by drone. So there are no trucks driving around inside the city delivering things. It's all like the drone will arrive now and deliver it, somewhere. I've seen demos for various companies that I think I saw the very first demo actually of the Amazon delivery drone. It's not completely clear. I don't know how that works. I mean, I suppose you have there's sort of it has to figure out where it's going to put, the package or something. I don't think it gets to come and knock on the door or anything. But anyway, maybe it calls something when it arrives. I don't know. But those are things which will affect kind of the way that people choose to structure things. Like, for example, imagine that everything's being delivered by drone instead of like people having cat flaps in their doors or something for cats. Maybe it'll become a thing that people want to have a drone flap in their roof that will be the place where, deliveries get made by the arriving, drone. It's hard to predict those kinds of things. But I think now in terms of objects that people have and kind of one of the things that's true about the objects we have is kind of there's a question. You can always tell, what's an artifact, what's a natural thing. These days, you can pretty much always tell that because you can, the thing that looks sort of more geometrically simple tends to be the object that we made. The thing that is more sort of elaborate will typically be the natural object. Not always true. I mean, you can have a perfect crystal made by nature that's a perfect geometrical shape, and you can have some very elaborately created industrial design that looks, that is quite elaborate that humans made. But the question is, will it be the case that the things that we make continue to look sort of understandable by us? And in a sense, there's part of the reason that things look understandable by us is because they were designed by us. And typically we don't have, we're not setting things up so that we just sort of do what, for example, nature does and let different forms evolve, and sort of the one that is ultimately the fittest for this environment might succeed and so on. We tend to just say, let's sit down as an engineer or industrial designer and sketch out what we want this object to look like. And so there's sort of this question of even if we, for example, were to say, okay, define a purpose. Let's say the purpose we want to define is, what's a good example? Well, I was going to say design a chair, but the point about a chair is, it's got a human sitting in it. And so the structure of the chair is very determined by the structure of the human, so to speak. If we said design a chair for a lizard, well, a chair for a lizard is going to look very different from a chair for a human. But maybe we have a different example. Let's say design a light fixture that will optimally, shine light around a room, let's say. Well, we might think, oh, well, we just put an empty bulb there, but oh, that's not going to work because it casts shadows and so on. We want some kind of diffuser, and we want, we need, the stand for the light is going to get in the way. Well, we can imagine there's sort of a different set, a whole bunch of constraints. If we define, we want the pattern of light that comes out to have this particular form, then we can say, okay, computer, for example, go find me the best design out of some whole set of all possible geometrical designs, the best shape that will lead to this particular distribution of light. And maybe the computer will come up with something that looks totally weird, has these different bulbs in different places and they're one's shining next to another and so on and so on and so on. And we might look at that thing and say, that's really complicated. No human would ever have come up with that design, but it's something that we can find in the sort of computational universe of possible designs. We can find this elaborate design, and that's the thing that the computer found that was the most efficient design, so to speak. And so one of the things that I think will probably happen is more and more of those kinds of things, where they are sort of most given a set of constraints. The most efficient design that satisfies those constraints is often not something simple. Sometimes it's something simple, but often it's not. And clearly, what matters is, did you get the constraints right? Let's say you define the constraints in a computational language, then are you setting things up so that you got the right constraints? If you've got the right constraints, now you can design that elaborate, sort of structure to satisfy those constraints. I mean, by the way, you can apply this kind of thing to lots of different domains. I mean, if you've got a certain set of constraints and you say, let's make regulations, let's make laws that achieve things with certain constraints. You can imagine, what possible law could you make that would, be some complicated thing with some taxes and commissions and this and that have some elaborate structure to achieve some particular constraint. If you get the constraint wrong, or if there's some unintended consequence, which it often will be, of the thing that you then build, well, then sort of all bets are off. But one of the things that I think is the case in the world in general is sort of, first of all, there's the process of design, which is going away from humans. And we're going to be able to find some optimal designs that might be things that to us humans look, how would you ever have thought of that? Well, no human did. And the other thing is things in the world that we sort of interact with through computers rather than directly ourselves. Like, for example, if you have some complicated set of rules about how something should work, and you're buying a thing and it comes with these different conditions and this and that and the other, it's like if they were fairly simple to state, a human would just say, okay, yeah, I'll press that button, I'll get that thing. But if they're very complicated, it's like, well, actually, you have to have a whole, computer figuring out, oh, do you do this thing or that thing, or do you set this parameter this way or that way, and so on. I mean, it's the same kind of thing in, in a car, for example, in a gasoline car, for instance. You've got things where in early days, it's like you put your foot on the gas and it just, some valve opens and you put more gas somewhere. But in today's world, that's a much more elaborate thing with fuel injection systems and computers, and it's a lot and sensors and so on. And it's something where there isn't a kind of direct story of kind of it was designed this way and so it works that way. There's sort of a computer in the loop that allows the system to work in a much more complicated way. And I think that will be an increasing story of what happens in the world, is that it's kind of us with our sort of general desire, make the car go faster, and then it's the sort of computer in the loop that's doing often very elaborate things to actually achieve the objective we want to achieve. And I think that's that's going to be more and more a feature of the world, that it's kind of a world that you can sort of only, that has a lot of things set up that are mediated by computer. I think the fact that there's sort of signage on roads, and the fact that we kind of, you can read the road sign and decide which way to go. Well, there'll probably become a time when there really don't need to be any road signs anymore, because everybody has a GPS. Most cars are self-driving, and it's like, who needs the signage? Who needs all these things saying, turn this way at this time? It's just like, just look at the GPS. And I think as sort of this computer-mediated layer in the world develops, things will probably change in terms of the way that things are set up. I mean, I remember when I was a kid growing up in England, there was non-decimal currency, which was, might have seemed completely crazy because it was very hard. Some things were convenient. There were 12 pennies in a shilling and 20 shillings in a pound and 21 shillings in a guinea and all kinds of things like this. It was, and, when I was a young kid, I remember sort of figuring out with great excitement that money didn't have to be non-decimal and you could actually make money be decimal. I remember some teacher telling me it's been this way for 500 years, it's never going to change. And like it was only a year later when it got announced, the UK is going to decimalize its currency. But one of the things I suspect, that decimalization happened in 1970. One of the things I suspect is that had it been delayed by another 10 years, electronic calculators came in 1972. Had it been delayed by another 10 years, probably it never would have happened, because everybody who was like, oh, I can't work out things with this non-decimal money, it's so difficult to work with. It's like, don't worry about it. You've got a computer to do it. You've got a calculator to do it. You don't need to worry that it's kind of weird and difficult to do calculations in. And so, that's a place where sort of if there'd been that layer, that intermediation by computer layer in one's interface with the world could have been set up somewhat differently. And I think those are some things that I can see being sort of happening is the increasing sort of computer layer that can allow different kinds of things to exist in the kind of raw world as it is. I think in terms of like homes and what they're like, the house that I have here, we built it like 20 years ago now. And there was sort of a question at the time, 20 years ago, what kind of home automation should there be, and what should one kind of be ready for in the future? And I suppose my big innovation at the time was just run empty tubes, empty conduit in the walls, because whatever kind of wires will be necessary in the future, you can run them through empty tubes. And that has been okay, except that, wireless technology is used for many things, although not everything. And that turned out to be a win. But if you ask, what's fundamentally changed? I mean, houses have become vastly more complicated over the years. I mean, if you look at kind of, a house from, 1,000 years ago or something, or 2,000 years ago, it's just the walls, and there's some openings for windows and things. And there's not all this elaborate stuff in the walls and air conditioning and electrical wires and maybe fiber optic cables and all this kind of thing. I mean, there's a higher degree of elaboration of what it takes to make a house. And when you see a house being built, it's kind of like the main framing of the thing can go up very quickly, but then there's all this detail of all this stuff and insulation and this, that, and the other that has to be put into it. And one of the things that one wonders is, will that just get more and more complicated? Will it actually get simpler because there are more things that can be kind of run? It's like, oh, you don't have to separately run, this kind of wire and that kind of wire, because they all got handled by, I mean, like you might imagine, oh, I've got to run a wire for my printer, or I've got to run a wire for my this, that, or the other thing. But actually, they're all sort of universal, that they all communicate through Wi-Fi, or they all communicate through fiber optics or whatever else. You don't need to have sort of separate wires for different kinds of things. I mean, it's a general trend that one sees with computers. It's like there are universal computers. That's a fundamental fact. That's sort of probably the most important scientific fact that's emerged in the last 100 or so years, is that it is possible to have a universal computer that you can program to do all sorts of different things. And that idea of universality is something that kind of increasingly is used elsewhere. Increasingly, things which used to be, oh, you make a particular machine to do this, it's more you make a general purpose machine and it can be programmed to do all these different things. Kind of brings up, another thing that for houses, for example, construction of houses is very much done by basically by people. And it's and there's a lot of complexity in the things that have to be done. And people say, well, when will it be the case that you can either just manufacture a house and just sort of deliver the pieces? People have tried doing that plenty over time, but it's still not the case that most construction is done that way. Or when can you have the robots do the construction instead? It's a difficult case for robots. It's not one of the easier kinds of things. I mean, it's worth remembering. So this question about general purpose things versus special purpose things, robotics is still pretty special purpose. I mean, you end up with a particular kind of robot arm that does a particular kind of thing. Now there's some, for example, to understand kind of the state of robotics, this thing about, can you pick up an arbitrary object? Can you make a robotic hand, and whatever the shape is, however heavy the thing is, however slippery it is, can you pick it up? And we humans at least seem to be pretty good at picking things up with our hands. Now, of course, there's a little bit of a trick to that, which is the things that exist in the world that are made tend to be made not, it's often the case that they were made intending to be picked up. So, we don't make a lot of things which are like very covered with spikes and very slippery and so on, that were just really hard to pick up. There's, the number of uses for things that are really hard for us humans to pick up is smaller. And so we tend to make things that are easier for, our actual hands as they're made and so on to pick up. And so when we try and use different kinds of materials that we might use in a robot, and we use different kinds of sensors and so on to sense whether you're touching things and so on, it's more difficult but that's an example of a kind of frontline challenge in robotics these days, is kind of the picking problem of, can you pick stuff up? And it's really hard, and that's not a solved problem yet. And so that kind of gives you a sense of what still is to be done in robotics and so on. I think that I've tended to think for a long time that eventually there will be general purpose robotics, where you have a thing that is maybe made from a large number of tiny components that sort of reconfigure themselves to be a different shape that can achieve a different purpose. And once there is general purpose robotics, that will change all kinds of things. And sort of, it'll change certainly the construction of things like houses, and probably the cost of constructing them. It'll change it'll presumably change lots of things about our everyday, everyday life. I mean, I remember a few years ago being at the annual Consumer Electronics Show, and there are all kinds of whizzy things there. But the thing for which there was the longest line and the most excitement seemed to be the laundry folding robot, which was not clear how well it worked actually. But that's the kind of thing where eventually there will be robotic ways to do all of those kinds of things. And I think that now, having said that, I know some kinds of sort of home automation of the different patterns of lights that you can put on, or the elaborate kind of I have to say, maybe it's just me, but I have not found. Even though I've had sometimes even some Wolfram language-based sort of home automation that's been set up, I've not found it as profoundly valuable in my life as one might have hoped. And it's been one of these areas where people sort of say, there's going to be more automation. You're going to be able to do all these things automatically. And it's like, well, yes, but it doesn't really matter much anyway, and it's hard to do and so on. So I'm not sure, but I think by the time there's really general purpose robotics, maybe by the time, for example, it's routinely the case that a robot can put things away for you, that will be interesting. And where a robot walks into a room, it uses kind of a visual diff. It says, this is what the room looked like yesterday. This is what it looks like today. Oh, I can see this, there are these visual changes to what's happened, and it kind of brings up in your thing, do you want to put this away now? You took this book out from here. Do you want to put that book away, back where it came from, so to speak? That's the kind of thing where we don't yet have that capability, but we presumably will, and that will probably change. And maybe there's the question of again, we've optimized kind of, well, like for instance, I've had a bunch of these robotic vacuum cleaners for ages, and I suppose some changes, made some changes because it's like, well, this piece of furniture, the thing is always going to get stuck there. So let's change that. And, one can imagine that just like in designing cities, if there's a different form of transportation, you end up designing things differently. So similarly with houses, if it's really important that the the floor robot or whatever can get from here to there, and it's really pretty easy to remove that strange mat that it always gets stuck on, or to build this little extra, the robot flap or something, then people will end up doing that. All right. Maybe one more thing. Oh, somebody's commenting here that since the world is now built around humans, would humanoid robots be the most general? That's an interesting issue. I mean, I think that it is certainly true that if you build a walking, robot that's 5 or 6 feet tall and has hands and arms and so on, yeah, the world has been built for things like that. And so for some purposes of robotics, that will be the best form factor. But of course there are things robots can do, like you could have a little drone flying robot that goes and does that thing about checking whether anything needs to be put away in your house. It could be the robot that is optimized with many arms, and the thing that has something that can sort of put itself up, to reach that highest bookshelf, so to speak, which a human would have a hard time with, and you have to get a ladder and this and that and the other. You could imagine a robot that has these optimized, legs that just extend up to be able to reach that, not very humanoid-like. And where you can imagine the sort of symbiosis of the little, drone flying robot that flies around your house and finds what needs to be put away, and then the robot that is, all arms or something that goes and in a better way puts things away. But yes, in terms of sort of the general purpose robot that is in the built environment, that is, houses and cities and things like that, it's very likely to be the case that something which is sort of humanoid in form is going to have an easier time navigating that environment. Now, of course, if it's like, okay, robot, go out in the jungle or go out in underwater or something like that, well, those are not human-built environments, and so a completely different form factor and structure might be the optimal one. But yeah, it's a funny thing that once technology gets built in a certain way, it tends to be the case that a lot gets built on top of the often rather arbitrary decisions that were made in setting up the technology in the way that it was set up. I mean, once a certain piece of infrastructure is in place in some form, lots of things get built on that, even if it was kind of a weird, even if it's almost sort of a weird thing that you would construct that way. Well, lots more to say here about obviously there's a lot of interesting questions about future technology and robots, and what happens when you have the home robot and you have all these ethical decisions. Should the home robot move the cat? If the cat was sleeping happily, what are the conditions for moving the cat? When is it ethical to have the robot, sort of push the cat into some corner? When is it, and what cat rights should the cat have relative to this or that? And those are things which, particularly if you leave, robot and cat home alone, what does what autonomous decisions should the robot make about what to do? Or, there are just endless, well, of course that comes up even more. It hasn't really come to pass yet, but I think it will come to pass with old folk before it comes to pass with young kids, of the robot that takes care of the person, so to speak, and what its kind of principles are in terms of what it should do and not do and so on, and under what circumstances. It's kind of like the famous question of, when you ask the self-driving car to drive above the speed limit, what should it do? And under what circumstances, and what does the law say about that? Well, it usually says, if you need to go above the speed limit for a really good reason, you can do it. How does the self-driving car assess? Was it a really good reason? To avoid an accident, to do this or that. The way that these things are set up now, it's very much, well, if the human thought this, even if the human was wrong, it's okay. But then when it's kind of an AI system, how does that, how does one decide whether it was reasonable for it to have thought that, and so on? All right, well, lots of interesting questions and things to discuss there. So we've gone from the atoms of space to cat-moving robots. Well, hope people have found this interesting. I always find these fun because you all get me to think about things that I don't normally think about, and it's kind of great exercise for my brain, at least, of thinking about all these different kinds of things and the connections between them. So please feel free to suggest topics, ask questions on our the form that we have out there, and look forward to being with you another time. So thanks very much.